Hi, good afternoon. Today we are going to discuss on a capacity-based seismic design philosophy. And this capacity-based seismic design philosophy is implemented in developing countries' seismic code, and the practicing engineers are using capacity-based seismic design philosophy in developing countries. This method is still further modified after 2000 and what is known as a probabilistic performance-based design. So today's focus of the discussion is to discuss the framework of probabilistic performance-based design philosophy. Then outcome of this framework is we get some probabilistic curve known as fragility curve, seismic fragility curve. So what are the characteristics of the fragility curve? What are the application? How to develop this fragility curve? What is the equations? And at the end, what is the use of this fragility curve is the focus of today's discussion. Before to go for in-depth about the performance-based design or capacity-based design, let me discuss what is the design philosophy adopted in Indian seismic code. In Indian seismic code, performance-based design is not implemented. It is not included in IS 1893, even the code was revised in 2016. But still, it is based on traditional strength-based approach. In the case of strength-based approach, we are calculating one force, what is called as a base shear, which is generated at the base of the column by this equation Z by 2 I by R and SA by J into seismic weight. And this particular force, we are designing the structure to resist this force. And we said that if the building resists this seismic force, that means the building is safe for the earthquake. So this is our design philosophy. Okay, so that means we are rely on only one force, that is the base shear. Okay, but at the other hand, we are not observing what is the damage pattern, what is the progressive failure, or what is the actual performance of the structure that is not included in traditional, that insight we are not getting from the traditional strength-based approach. In strength-based approach, again, the structure is not designed for the actual force. Okay, to explain more detail, let's refer this particular figure. Now, this is the force, which is the actual seismic force to which the structure is going to subject. It is subjected to this force, which is known as the actual force. But in this design philosophy, the structure is designed not for this actual force, but this is designed for a force which is lower than the actual. So this is the design force. That means obviously we are applying some reduction factor to the actual force. So two values are given of the reduction factor R. That is either 1 by 3 or 1 by 5. That means we are designing either 30% of the actual force or 20% of the actual force. It means that since we are not designed for actual force, we are designing for lower than this. Obviously, structure will yield. There will be yielding of the structure. And after yielding of the structure, then the structure enter into the inelastic range. So this is inelastic behavior of the structure. So as per the seismic resistant design is concerned, this is the expected behavior. Always the structure should deform in inelastic range, because inelastic range is the cyclic in nature during earthquake, and cyclic behavior of the structure dissipate the seismic energy, and therefore this is the expected behavior. While as this is the elastic range of the structure, and elastic range of the structure, elastic nature or elastic behavior of the structure is not cyclic. It is non-cyclic. So therefore, it is not dissipating that much seismic energy. So only the focus is on the inelastic range of the structure. Okay. Now, what is the change in performance-based design? Now, in a performance design, after doing so, in performance design, more focus is on inelastic range of the structure. So why the more focus on inelastic range of the structure? The answer is simple, because inelastic range of the structure or the structural collapse occurs in the inelastic range only. So therefore, we should have to calculate the inelastic response of the structure. That means how much is the deformation. Okay. And so this is the inelastic range of the structure. This is the inelastic range of the structure. That is after yielding. What is the deformation in the structure? The structure in which more deformation, that means structure is said to be more ductile in nature. And ductile behavior of the structure dissipate more seismic energy. So this is the basic principle of capacity-based design. At the end of the calculation, that is both responses, that is elastic behavior as well as inelastic behavior of the structure is studied in the case of capacity-based design or perform-based design. So in the figure, there are three curves are shown. So curves for three buildings. One is old building, second is a new structure, but the reinforcement detailing is not as per the ductility provision. So this is second curve, and this is the expected behavior. This is the capacity curve for the new structure, which is designed by a recent seismic code, and the ductility, reinforcement ductility is as per the ductility code. So this is, we can easily differentiate the response or the response of the structure. The first old structure, okay, it shows very weak response in elastic range. So that means after yielding, the structure is immediately going to collapse. So this is called the brittle behavior or weak response. Area under curve is also very, very less. So this dissipate very low seismic energy. Similarly, curve number 2. Now it is resisting more force. It is resisting more force comparative to the first one. Okay, but again here, after the yielding, again the response of the structure is very poor, and therefore this is also not dissipating that much seismic energy. And this is also not the expected behavior. So third is the expected behavior, in which after inelastic range, the structure deforms in a large way, and therefore dissipation of the energy is also more. And this is the structure which is resisting larger force comparative to this. So this is the outcome of capacity-based design. So that means we can able to calculate the elastic response as well as inelastic response, how much energy is dissipated during earthquake, and the structural behavior during earthquake is brittle in nature or ductile in nature. So that also we can study from the capacity-based design. Another feature of the capacity-based design is that, perform-based design is that, we come to know the failure pattern of the structure. Okay, so failure, as I said, failure occurs after yielding only. Okay, so what type of failure it is, whether it is a flexural failure or whether it is shear failure or it is axial failure, that also we can observe from this particular design philosophy. Again, the sequence of the failure in the that is sequence of the failure is from bottom story toward the top story or top to bottom story, whether the columns are failing first or beams are failing. All the damage pattern on sequence of the damage also we can, all the information we'll get from the capacity based design. This is the beauty of this particular method. Not only this, okay, so in capacity curve, we can also able to estimate the stiffness in inelastic range, then stiffness in the inelastic range. Also, we can able to investigate the ductile capacity of the structure. Okay, so all these features which actually required for further calculation, all are possible from the perform-based design. Thus, perform-based design, by using perform-based design, we can able to calculate elastic as well as inelastic behavior of the structure. Then we can able to learn failure pattern, which are the weaker elements which fails first, and what is the sequence of the failure. We can also observe the ductile range of the structure. Second, what is the energy dissipated during the earthquake, that also we can observe or can able to estimate. then deformation at any point we can able to this thing, and obviously the failure pattern. All this information, that means up to date, all the information will get only from this capacity based design. Now capacity based design is applicable for old structure as well as for the new structure. If we implement this method for the old structure which is deteriorated structure and which is weak in seismic resistance capacity, then we can decide some retrofitting strategies. That means by means of perform based design, we can identify the weaknesses in the structure, deficiency in the structure, whether that weakness or deficiency is global or it is at the local level. And from that we can decide the retrofitting strategy, that is the application to older structures. Similarly, we can apply it to this methodology to the new structures, especially critical structures like hospital is there, nuclear power station, which actually has the great importance and social importance is there. And if we implement to these particular critical structures, then we can raise the performance of the structure to the severe earthquake. So earthquake resistant design, for that also it is required. And such type of retrofitting strategies we can, for the old structure, we can decide from the perform based design. Now, this perform based design, what is the current trend worldwide, that also we'll discuss. As I said, that is before 90s worldwide, only one design philosophy was in practice. Okay, so that is known as a strength-based approach. So that is in the case of strength-based approach, only the strength of the structure is taken into account. And if the structure is resisting that particular base shear value, the structure is said to be safe. At that time, perform-based design was there, but it was not taken that much seriously by the researchers as well as by the practicing engineers. But after 2000, after 90s to 2000, there was many changes happened in the seismic design code, especially in the developing countries. And the reason was that in between these 10 years, especially in USA, the structures were subjected to a very massive earthquake. One example is 1994 Northridge earthquake. This particular earthquake is also known to be a historical code-changing earthquake. And after this, during that particular earthquake, not only concrete buildings were collapsed, but steel buildings were collapsed, and the brittle collapse were observed in the beam column joint. And therefore, the researchers and the practicing engineers became very serious, and whatever the weaknesses in the strength-based approach that come on the surface, and they sit together and they were very much serious about the performance design. And then the performance design came into the seismic code. So these are the seismic codes: ATC 40, FEMA is there, Federal Emergency Management Agency 356, ASC 41. So these are the codes, American codes, in which the performance-based design was included, and the practical engineers started to use this particular method. But again, it was observed that there are still this method need to improve, modified, because it is performance-based design is, by means of this, we can observe the failure pattern. We can observe the performance of the structure for that particular earthquake. It is true, but still there are some uncertainties are there which are not coming into anywhere in the calculation of performance design. So what is uncertainty? Which are those uncertainties? So the uncertainty with respect to ground motion and uncertainty with respect to building capacity. So uncertainty with respect to ground motion means the ground motions or earthquake waves are very uncertain. We cannot predict anything about the futuristic earthquake, how it comes, what will be the frequency, duration, then amplitude. We cannot predict anything. So this is also one kind of uncertainty. And second, when earthquake hits to the structure, how the structure behaves, About the capacity, we are not much more means what is called as a deterministic with respect to this thing. So actual behavior, it is very difficult to judge. And the concrete, we know concrete is very uncertain material, and how the concrete will respond to that. So uncertainty with respect to concrete behavior or structural capacity behavior is the uncertainty. So therefore, the method which is accounting to this uncertainty is the method what is called as a probabilistic perform-based design. So this is the advanced step to the perform-based design, and thus probabilistic perform-based design comes into practice. Okay, now this probabilistic assessment framework, seismic assessment framework, many researchers were worked to develop the framework, and one of the pioneer researcher is a Cornell. He is from Berkeley University, California, and this particular framework consists of 4 steps. First step is a hazard analysis. Number 2, structural analysis. Number 3, damage analysis, and number 4 is the loss estimation. Okay, so and this particular framework should be completed in the sequence: step 1, step 2, step 3, and step 4. And the outcome of this probabilistic assessment framework is the fragility curve, what is called as a probabilistic curve, which is the focus of today's discussion. Okay, now this is the outcome of the probabilistic framework. Now, fragility curve, its definition, a fragility, seismic fragility curve, it's showing the probability of exceedance of a certain damage state for a given seismic intensity. Okay, in short, in simple way, I will explain here. So it is a probability, it is the curve on y-axis probability, on x-axis it is a seismic intensity. It is a seismic intensity on x-axis. Seismic fragility curve is developed for a different damage states. Whenever the structure is subjected to earthquake and it is subjected to lower intensity earthquake, then there will be a mild damage. The name is, for example, slight damage. Second, when the intensity increases, then there will be a moderate damage. When still intensity increases, it is called as the extensive damage, and lastly, it is called as a complete damage. So these are the names given to the different damage states, and fragility curve is developed for each damage states. So in the figure, it is slight damage, moderate damage, extensive damage, and complete damage. In some of the seismic codes, only 3 damage states were defined: immediate occupancy, life safety, and collapse prevention. Some of the researchers like Wamasco, so he proposed 3 damage states. Okay, so that is first immediate occupancy, life safety, and collapse and global instability. So definition, that is description of the damage states, as well as the this value, what is called as a quantitatively and qualitatively, the values, the description of these damage states are different in different codes and in different research papers. Now, this particular fragility curve, basically there are now to develop this fragility curve, there are 2 things. One is the center point of the fragility curve, which is called as a median value of the damage states. Okay, and second, the slope of the fragility curve, okay, which is called as a standard deviation. So median value lambda, and second is the slope value beta. These are the only 2 parameters required to estimate, and these are estimated from the structural analysis. So perform nonlinear analysis, and from that calculate these 2 parameters. Then there is an equation to develop this particular curve. Just put these 2 values, we'll get the fragility curve. Now, the applications of the fragility curve, we can develop the fragility curve for any structures. Okay, like nuclear power plants are there, or it is bridges are there. Then buildings are also there. then dams are also there, and other critical structures. So it is possible to all type of the civil engineering structures. For a new structure, I will be the old structure. Now this is the equation to develop the fragility curve. So it is P stand for probability. So it is probability of exceeding the limit for given seismic intensity like spectral acceleration is equals to phi stand for standard normal distribution. ln is nothing but natural logarithm of seismic intensity minus natural logarithm of lambda divided by beta. So here there are only two parameters seismic. We have to calculate beta and we have to calculate the lambda. Once we calculate these two, very easily we can develop the fragility curve. And just lambda value and beta value changes for different damage states. Okay, and these are to be estimated from the structural analysis. Now, what is the structural analysis that we'll see? Okay, now probabilistic assessment framework. First step is the hazard analysis. Hazard analysis in simple way, it is nothing but the location or the area where actually the structure is located and we are developing the fragility curve. The seismicity of that location, the user must know it. That is, what are the past earthquake, what were their effect on the structures, what are the failures due to those massive earthquakes. Then what is the type of the strata, whether liquefiable soil is there. Okay, so that is with respect to seismicity, all the parameters, study of the all parameters is nothing but the hazard analysis. Sometimes we require to take the help of the geologist. Then second is the structural analysis. So this is the most important step because structural analysis data, we are required to calculate the standard deviation and median of the fragility curve. Now, in the case of structural analysis, actually what is required to do, we have to use some softwares. We have to take the help of the software. Many softwares are doing this seismic nonlinear analysis. One software is very good in nature, what is known as the SAP 2000, developed by CSI. So SAP 2000, it is possible. So in this particular software, first of all, create a model. First step is a create model, normal model. Then convert that model into nonlinear model by assigning the nonlinear properties to each and every elements. That is step number 2. Step number 3 is after creating nonlinear model, then perform nonlinear analysis. Okay. And after doing the nonlinear analysis, then there will be a damage analysis. There will be some damages and we should have to note the damages in systematic way. So damage analysis. And finally, 5th step is development of the fragility curve. These are the steps are there. Okay. Now, in between, that is convert the regular model into nonlinear model. That means we have to assign some nonlinear properties to the beam column. What are the main important element of the structure like shear work? Otherwise, structure will not deform in the inelastic range. Structure will remain elastic only, or it will show only linear behavior. Okay, so therefore it is required to assign the nonlinearity or nonlinear properties. Okay, now nonlinear properties are 2. First is called as the material nonlinearity and number 2 is called as the geometric nonlinearity. Both nonlinearity is required to assign. Material nonlinearity, what is the meaning of this? The relation of stress and strain across the section, material stress and strain across the section, the relation is nonlinear. We have to define as a nonlinear relation. And to assign this nonlinearity, that means how to assign this nonlinearity to the structural element, there are 2 approaches. One is that lumped plasticity approach and second is called as a distributed plasticity approach. In simple way, I will explain. Lumped plasticity approach means, suppose this is a beam. In the case of lumped plasticity approach, the nonlinearity is assigned only to some specific areas, some specific zones, especially for a beam and column. We have to assign the nonlinearity at the ends only. That is called as lumped. We are not assigning to for complete length of the element or member. While as in the case of distributed plasticity, what is second option? That means we have to assign the nonlinearity for a complete length of the member. If the beam is there, assign the nonlinearity for complete length. If it is a column, assign the nonlinearity for completely column. So this is about the material nonlinearity. In the researcher have shown that either you implement lumped plasticity approach or distributed plasticity approach, the result seismic response of the building, the results are not much difference. So whichever convenient to the users, so adapt that particular method to assign the nonlinearity, material nonlinearity. Second is called as the geometric nonlinearity. Is called as the geometric nonlinearity. It means that the ratio of the relation of material strain and displacement, this relation is to be nonlinear, and it is related with shape change. In seismic analysis, nonlinear analysis, this geometric nonlinearity is well known as P delta effect. Okay, later on we'll discuss about the P delta effect. Okay, so this is about the nonlinearity. Further discussion of nonlinearity is that, see, so in the software like SAP 2000, so this is the figure, this is the sketch of the nonlinearity is assigned to a beam and column. Now different color hinges, that means we have to assign just hinges, auto hinge to this. Ready-made hinges are also available, right? So there are three types of the hinges are available. So that is either flexural hinge, then shear hinge, and auto hinge, axial hinge, sorry, axial hinge. Flexural hinge addresses flexural failure in the member. Shear hinge addresses shear failure, and axial hinge addresses the axial failure in the structure. Okay, so that means if the diagonal member is there, diagonal member, so how the diagonal member fails during earthquake? For the axial loading. So for the diagonal member, we have to assign the axial hinge only. Okay, for example, beam and column. So beam and column fails either in flexure or it fails under shear. So therefore, for the beam and column, we have to assign the which nonlinearity? Flexural as well as shear. And you may ask the question that why the nonlinearity in the case of lumped plasticity is to be assigned at the ends only. Answer is simple. So it is shown in the figure, in the photo. This is the photo of the past earthquake. Column collapsed. Where it is collapsed? At the ends only. So that means there are many photos like this. Past earthquake, all many times, almost 70 or 80% or more than that. The beam and column fails at the ends only during earthquake, during massive earthquake. And this is one of the evidence from the evidences. So that means ends are very critical and we have to focus the failure of these members at the end. That is the first. And second, the frame subjected to lateral load. The bending moment is maximum at the ends of the member. So flexural stresses are concentrated at the ends and therefore the element will likely to be fair at the ends only. And therefore, in the case of lumped plasticity approach, the nonlinearity is assigned at the ends. Okay, now the shear wall is such an element which is area element or shell element to which the nonlinearity is applied by both way. Either we can apply it by lumped plasticity approach or we can apply it by a distributed plasticity approach. Okay, that means the nonlinearity is assigned for a complete area. In SAP 2000, there is one command, what is called as a multi-layer shear element. By using that particular command, we can assign the nonlinearity to the shear wall. Okay, and this is the figure about the geometric nonlinearity, what is called as a P delta effect. Okay, so in the case of P delta effect, just to understand this, remember the figure. Here the column is subjected to during earthquake. There are two loads are there. First is the lateral load H and the gravity load, which is always present on the column, on the structure. Now, because of these two loads, what are the moments at the base? Okay, there are two moments. First, this is the movement due to the lateral force, that is force into height of the structure. It is clockwise movement. And second, secondary movement, it is P, that is axial load into the sway. Okay, this is secondary movement known as P delta movement, and this is very what is called as this is causing more critical effect on the behavior of the column. Okay, that means just we'll see in this way also. If the column during earthquake, it will sway like this, it will buckle like this, and during that state, it is subjected to a gravity load. So what will happen? If the column is already buckled and we applied the gravity load is always present, what will happen to the behavior of the column or response of the column? Column will still bear. So it will show a softening behavior, softening. That means there is a reduction of the stiffness. So in one line, we can say that because of the P delta effect, because of this secondary moment, the column behavior or the structure behavior becomes soft. That means stiffness is going to reduce. Now, this effect is also should be considered in the analysis. So that means stiffness matrix must be updated. Okay, so this reduction in stiffness is also shown in this particular figure. So this is a P delta effect. So this is about the nonlinear definition of the nonlinearity and how to assign the nonlinearity. Now, after that, after assign the nonlinearity, perform the nonlinear analysis. Okay, why to perform nonlinear analysis? By performing nonlinear analysis only, we can able to calculate the inelastic response of the structure and what is the failure mechanism in the structure. So therefore, we have to perform the nonlinearity. There are two methods traditionally. First is known as static pushover method. Okay, and second is a time history method. In the case of static pushover method, the structure is pushed on one side, until the failure. So while pushing, we have to apply lateral force. That is earthquake-induced lateral force are applied on the structure. Okay, and therefore the structure will undergo different stages. Okay, and then up to the failure. So that is the simple principle of the static pushover. But this is a what is called as a theoretical case it is. Okay, and this particular method to be to be used only when the structure is a regular type of the structure. That is first mode dominated structure. So this static pushover, further there are two methods bifurcated. One is capacity spectrum method, which is documented 8640. By using this method, capacity spectrum method, we are calculating the performance point. While a displacement coefficient method, which is documented in FEMA 273, by which we are calculating what? Target displacement. Okay. Then next, time history analysis, which is the most realistic. Why? Because in this time history analysis, we are actually applying the ground motion at the base. So this is the case, is real case. Okay, so this is a real case. And then, but it will require more time. So computationally expensive this method, but it is most correct. Okay, and advancement of this method is the incremental dynamic analysis. Advancement is the incremental dynamic analysis. This incremental dynamic analysis, which was developed by this researcher known as Wamasco in his PhD research in 2002. All these methods are to calculate the inelastic response of this structure. Then once the analysis is over, then there will be damages in the structure. Okay, and these damages should be quantified. Okay, quantified, as well as the damages, it should be defined. This thing. Different names are given as a previously also I mentioned: slight damage, moderate damage, extensive damage, and complete damage. Okay, so these are the different damage states. So this damage analysis, this comes under damage analysis. Damage analysis, and this is the third step in the probabilistic assessment framework. Now this is the description of the damage states. Description, that means definition. So that is, for example, immediate occupancy. This immediate occupancy, what is meant by immediate occupancy? It is minor headline cracking, limiting yielding, possible at a few locations. Okay, so this is the description of the damage states. Okay, of 3 damage states. Okay, and so this is defined in different codes. Okay, so these are the relevant codes in which the definition of these damage states is given. And this is the damage quantification. Okay, because in the analysis, in the software, how we can say that is the immediate occupancy has been occurred. So the first example just I will give, the slight damage. Okay, the slight damage is said to be occur when interstory drift is 1%. Okay, where it is given in these particular relevant codes: FEMA 356, ASC 41, then ASC 207, ATC 58.2. Okay, then moderate damage is said to be occur when interstory drift is 2%, and extensive damage is interstory drift is 4%. Okay, so that means the user has a choice to use the different damage states. Okay, different damage states, and which values to be considered, or which code to be considered to define the damages. Okay, so that is user's choice. And after that, having a lot of analytical results from the nonlinear analysis, especially from the incremental dynamic analysis, then using that particular equations, develop the fragility curve. Okay, in next my videos, in detail, I'm going to explain, I'm going to show how the fragility curves are developed from a incremental dynamic analysis. So first of all, I will explain in my next video about the incremental dynamic analysis. Then Excel sheet I will explain about the development of the damage state. Okay, so this is the end of today's discussion. In conclusion, this probabilistic assessment framework, which is this advancement in the performance-based design. So what are the steps? Develop just I repeat, develop a regular model in SAP 2000 like software, then convert that into nonlinear model by assigning the nonlinear hinges, then perform nonlinear analysis, either pushover or time history analysis, then damage analysis, decide some damage states. Okay, right? And then develop the fragility curve. Okay, so thank you for patient listening. Thank you.